Okay, good morning. Any questions about any of the topics we have covered so far? We covered node voltage analysis, theory and example, and then also a little bit of the concept of a supernode. Any questions from anyone online? Okay. All right, then let's continue with the second analysis technique, which is mesh current analysis. Okay, mesh current analysis. So node voltage analysis, we apply KCL to generate our equations. In mesh current analysis, we apply KVL to generate equations. Okay, KVL. So first step is identifying the meshes in the circuit. Stated earlier in one of the previous classes, a mesh is a simple electrical loop. Right? A mesh is a simple electrical loop that does not contain any loop inside it. A loop is a closed pathway where current can flow through. So identifying meshes is relatively straightforward. Start at a point, you find a loop, and there should not be any other loop inside it, and that's a mesh. So as we see here, we have mesh 1, mesh 2, and mesh 3. We have 3 meshes, okay? And just as a refresher, each of these meshes is an electrical loop, but there are various other loops in it. If you combine mesh 1 and mesh 2, that is an electrical loop. A combined loop like M1 and M2 contains M1 and M2 inside it. And so this loop right here, let's call it L1. L1 is not a mesh because it contains other loops inside it. Okay, L1 contains M1 and M2, so it is not a simple loop. Similarly, we can take this, and just for explanation purposes, let me label it as L2, loop 2. Loop 2 contains M1 and M3 inside it. And so loop 1 and loop 2, neither one of them can be considered as meshes. Meshes are simple loops, and simple loops mean they do not contain any other loops inside them. Okay, so as I said, identifying is straightforward. Our brains can easily visualize a closed pathway. And so we have M1, M2, and M3. Again, labeling is up to you. You can label it anything you want, A, B, C, X, Y, Z, doesn't really matter. Okay, so we have a mesh, and the next step is to assume a mesh current that is flowing inside that mesh. Now, mesh currents, again, thinking back to a few lectures ago, when I introduced the concept of nodes and meshes, I stated mesh currents are hypothetical. They are theoretical. They do not exist in real life. Okay, mesh currents are solely for the purposes of analysis. Okay, as you can see here, we have a mesh current in each one of these meshes, I1, I2, and I3. Now, these are assumptions on our part. Okay, so mesh currents are assumptions. You can assume a clockwise direction or a counterclockwise direction. Doesn't really matter. It's similar to the assumption of a reference node for node voltage analysis. Okay, in node voltage analysis, we assume any one of the nodes in the circuit to be a reference node. So in the same way, we can assume either a clockwise or a counterclockwise direction for our mesh currents. Just out of habit, out of practice, and to be consistent, I always choose a clockwise direction. That's my personal preference. And I choose a clockwise direction for all mesh currents in the circuit. It is, of course, possible to mix and match. You can choose either clockwise for one and then counterclockwise for the next mesh, that is absolutely fine. It has no bearing whatsoever on your final answer in terms of like correctness. Okay. As long as your assumptions stay consistent throughout the entire analysis, your answers at the end will always turn out to be correct. Okay. So once you make an assumption at the beginning of the problem, it remains the same till the end. Okay. So what do we do next? If we have a mesh current flowing through a resistor, let's say if you have a current flowing through a resistor, it will cause a voltage drop. It will cause a voltage to appear across that resistor. And so we apply KVL to sum up these hypothetical voltages. So let's take mesh 1, for instance. In mesh 1, we have a voltage source. We have a resistor named R2. And then we have a second resistor called R3. And that's M1, mesh 1. Current I1 is flowing clockwise. Right? I1 is flowing clockwise. So now we have the voltage source, right? VA. And now I1 will cause a voltage to appear across R2 and R3. So we can write, or we can state, that the voltage drop across R2 would have a plus on the left because that is the point of entry, and a minus on the right because that is the point of exit. Similarly, R3 will have a voltage drop with a plus sign at the top and minus at the bottom. And of course, that is due to the point of entry being at the top. All right, let's take a pause. Let me know if you have any questions. Any questions from anybody online? Makes sense thus far? Straightforward enough? Okay. But here is the difference between node voltage and mesh current. Okay. In mesh current analysis, again, we have to keep in mind, and I'm repeating the same thing again, mesh currents are hypothetical. So if you have a shared branch, like we do with R2 and R3, and by shared branch, I mean that component or those components are shared between two meshes. Okay. And as you can see in the figure, R2 is shared between M1 and M3, right? And R3 is shared between M1 and M2. And if it is a shared branch, then you have shared currents. And so R2 has I3 coming from the right. Again, that current direction is due to the assumption we made at the beginning of our analysis. I3 is clockwise, meaning it is coming into R2 from the right. I1, of course, is coming from the left. The same thing with R3. R3 has I2 coming from the bottom. Okay, and again, those current directions are due to the assumptions we made at the beginning of our analysis. Now, what does this hypothetical current do? Well, even though it's hypothetical, the basic principle still remains. Current flowing through a resistor causes a voltage drop. So I3 coming from the right causes a voltage drop in R2. Where is the plus and the minus for R2 due to I3? Is the plus sign on the left of R2 or is it on the right of R2? Any guesses? I1 enters from the left for R2, so plus is on the left. I3 enters from the right, so plus sign is on the right. Seeing a plus and a minus this way. Same thing for R3. Enters from the bottom, so plus at the bottom, minus up top. I'll let that sink in for a few seconds. Think over that. And let me know if you have any questions. Any questions about this concept? Yes. So are you talking about this? R2? So what was the question? Okay, so the question being asked is the plus and the minus signs that are outlined, they are the only for the currents? And the answer is yes. It's the only for the mesh currents that are flowing through those resistors. Nothing else. Yes. Yes. So the question being asked is, in essence, I think what is being asked is they are hypothetical, right? Is that what you're asking? So the question being asked is, are the voltages and the currents hypothetical? And the answer is yes, they are hypothetical. They are not real. And that is going to be my next explanation point. Does anyone have any other questions before I proceed? Yes. So yes, the loop, are you asking whether we are using KVL? Well, right now we haven't reached the stage where we apply KVL yet. Right now we have just assumed the current direction and we are establishing the voltages that appear due to those currents. Okay. So now here's the important point. Electrical voltage. What is the definition of voltage? Voltage is the difference in electrical potential between any 2 points, right? If both points are the exact same potential, then there is neither a plus nor a minus. Hence, the voltage between the 2 points is 0. Hence, there is no current flowing through it. Okay. In our case, in mesh current analysis, we assume a current. We assume a hypothetical mesh current. Hypothetical mesh current I1 is flowing from the left. Now we are talking only about R2. Okay. We are only talking about R2. So we assumed I1 at the beginning of our analysis. I1, I2, and I3. And you're talking about R2. I1 is entering R2 from the left. So it logically follows that the left end of resistor R2 is higher than the right end. But at the same time, we have a hypothetical current I3 moving in the opposite direction. So we are saying this end is also higher, which realistically or real life is not possible. Does that make sense to everyone? Right? I2, I1, and I3 are not real. Again, I1 and I3 are not real. They're hypothetical. They're purely theoretical. Okay, it is only for the purposes of theoretical analysis. We assign I1, I2, I3, and we assume a direction for those. And of course, in real life, you can never have 2 points, one higher than the other, and at the same time, we are saying that the other point is higher than the other. It's just not possible, right? Plus and minus simply indicates which end is higher. Okay, so if I'm saying R2 left end is higher than the right end because of I1, at the same time, we cannot have the right end higher than the left. So it's purely hypothetical. Now, the point of this is that we are writing equations, okay? So the point is that we have to factor in those hypothetical voltages into our equation. So let's go into the next step, which is applying KVL, Kirchhoff's voltage law or loop law, and then sum up the voltages in M1. Okay, apply KVL to mesh M1. If you apply KVL, what do we see? We have 3 voltages. We have VA, we have VR2, and we have VR3, summing up to 0. And since we are referencing M1, then we take the direction of the mesh current for I1, and we sum up the voltages in that direction. So I'm summing up the voltages in a clockwise direction. So I would have minus VA plus VR2 minus VR3 equal to 0. And again, this goes back to the purpose of those earlier homeworks. Students need to be able to apply KVL, KCL quickly, correctly, and efficiently. Minus VA plus VR2 minus VR3. Yes. Oh, sorry, it's plus VR3. You're correct. Plus VR3. Yeah, both voltages are positive from the perspective of I1. Okay, since we are in mesh 1, we are taking I1 as positive. And now here's the part that we have to be careful about. We apply Ohm's law and express each voltage, each resistor voltage in terms of the mesh current. Okay, so minus VA because that's the source, and VR2 is due to R2. V equals IR. In this case, it will be I1 minus I3 times R2. And here, it will be I1 minus I2 times R3 equal to 0. So let's take a pause while you think over that. Let me know if something doesn't make sense. Any questions? you'll see why it is I1 minus I3 and I1 minus I2. Because the currents are flowing in opposite directions. If they are flowing in the exact same direction and you're adding up the voltages in that direction, it would be I1 plus I3 and I1 plus I2. So the signs, the plus and minus signs for the currents are due to the assumptions we made at the beginning of the problem. And when we get to the second mesh and the third mesh and we write our KVL expressions, those equations will balance out. Okay. Right now we have I1 minus I3 for R2 and I1 minus I2 for R3. If there are no more questions, I'm going to go ahead and apply KVL to mesh 2. Any questions? Okay. All right, let me draw out mesh 2. So mesh 2 has a voltage source here at the top. Okay, R3, R4. This is VB. And we have I2 flowing in a clockwise direction. I1 coming from the top. And that's it. We have I3 at the top flowing through VB. But we don't need to do anything about that because it's a voltage source. We can add that voltage source directly. And this is M2. So where are my voltage drops now? I got a plus here, a minus here, plus up top for R4, minus at the bottom. And then R3 is shared. And so we got a plus and a minus due to I1. Now let's apply KVL. We apply KVL. I have 3 voltages. VB plus VR4 plus VR3 sums up to 0. VB is a voltage source, so it stays as it is. VR4 is I2 times R4, and VR3, here's the difference. It's I2 minus I1 times R3. So write it down, think over it. Let me know if you have any questions. Any questions? Does it make sense? So what would happen if you choose the opposite direction for just I2? What changes in mesh 1 and what changes in mesh 2? So here, let me bring this up again. Scroll up, I mean. So if I2 was opposite, how would it change mesh 1 equation? It only affects R3, by the way. So if it's coming down, it's in the same direction as I1. If I2 is coming down, plus at the top, minus at the bottom. Exactly. So it would not be I1 minus I2, it would be I1 plus I2. And the same thing will be implemented in mesh 2. However, if both of these are coming down, sorry, R3 here. If both of these are coming down, I would have a plus here and a minus here. Instead of I2 minus I1, both of them would have a negative sign. It would be minus I2 minus I1. Right? It's going in the opposite direction. So this would be minus I2. This is already minus I1. So you'd have two positives or a double positive here in mesh 1, and you'd have double negative in mesh 2. And hence your equations would balance out. And that goes back to the point I made at the beginning. It doesn't matter what you choose as the direction for your mesh current. You can choose clockwise, counterclockwise. You can mix and match, have one or two currents as clockwise, the other one or two currents as counterclockwise. Your equations will always balance out. Okay, so let's take a pause, let that sink in. Let me know if you have any questions. Typically for consistency, I always choose everything as clockwise. So that keeps things simple. When I go into a mesh, the mesh current, when I apply the KVL, the current in that mesh will be positive. Anything outside and opposite will be negative. All right, any questions? Any questions from anyone? Okay, all right, then let's write the equation for the last one, and that is mesh 3. So for mesh 3, R2, R1, and I have I3. And I1. And so I'd have 8 plus and a minus for R1 this way, and 8 plus and a minus for R2 this way, plus and a minus this way. And now apply KVL, my expression would be VR2 plus VR1 minus VB equal to 0. VR2 is the only one that is shared. So I'm going to write I3. Because I'm in mesh 3, I3 is positive, minus I1 times R2 plus I3 times R1 minus VB equal to 0. And those are my three equations. At this point, we plug in all the known values, we reduce the circuit, we reduce the equations to obtain a set of linear equations. You solve them with any method you choose, and you obtain the answers for the mesh currents. Once you obtain the answers or the values of the mesh currents, you can find any other quantity in the circuit. Let's take a 10-second pause, actually a longer pause while you write it all down. Think over that. Let me know if you have any questions.
I have a quick question.
Yes.
So how come I2 is not used for the KVL in M3?
Okay, so it's a good question. Let's go back to the main diagram. Okay, so the question being asked is, how come I2 is not used for mesh 3, even though I2 is flowing here, right? So let me make and note the connection right here. All right, we have I2 flowing here. So the question does actually make sense, right? VB is shared between I3 and I2, right? You're referring to VB, correct?
Yes.
Okay, well, we are generating equations by applying KVL. KVL means you're summing up the voltages. VB is a voltage source. We already have the value for VB, so there is no need to express or take I2 into consideration. And that's the answer. Does that make sense?
Yeah, thank you.
And of course, there's also the case where we'd have a current source. And what do we do if we have a current source in there? Well, there's a workaround for that too. Okay. And again, this I1 plus I2 or minus I2 only applies to resistors that are in a shared branch that would have two mesh currents flowing through it. Okay, any other questions? Okay, so let's recap the steps. Identify all the meshes, assign mesh currents, and assume the current direction. Okay. Assume clockwise or counterclockwise, it doesn't matter. Okay. Then you apply KVL to each mesh. You write out the voltages, apply Ohm's law, and express each voltage in the mesh in terms of the mesh currents. If you wish to keep things simple, be consistent, choose all currents in the same direction, meaning all currents as clockwise or all currents as counterclockwise. That way, when you are writing KVL equations for shared resistors or shared branches, the dominant current, meaning the mesh that you're analyzing, is positive. Any currents that are outside the mesh are negative. That's it. And that would keep things straightforward. Make sense? Okay. Ready to go to an example? All right. So, question being asked is solve for all mesh currents and resistor voltages. Let's look at the circuit. 3 voltage sources and 4 resistors. Okay, 3 voltage sources and 4 resistors. So let's do this first. Let's assume and apply mesh currents in the circuit. We got I1 and we have I2. And I'll call this mesh 1 and mesh 2. Okay, and all the values are given. All the resistor values are given, and the voltage source values are also given. So I'm going to write the values right next to the components. So let's see. VA is 10 volts, VB is 9 volts, and VC is 1 volt. R1 is 5 ohms, R2 is 10 ohms, R3 is also 5, and R4 is also 5. Okay, so let's draw out mesh 1. In mesh 1, I have 4 components, VA, VB, R1, and R2. So let's draw those out. And I also request students, whenever they are working in a quiz or an exam, to create diagrams that are large. By large, I don't mean just drawing large, meaning occupy a larger space, okay, as I'm doing right here. What that does, it allows us to actually make notations on the diagram. So my components are the same size. The space that my diagram is occupying is large. Okay, VA plus minus, VB plus minus, VA, VB, R1, and R2. Okay. We have I1, we have I2 coming up from the bottom, causes a voltage drop, plus minus, and minus plus. Okay, R2 is the only shared resistor between M1 and M2. So things are relatively straightforward. Does the setup make sense? Right, we have a hypothetical mesh current, I1, and I2 is outside. Now we will apply KVL. Once you apply KVL, I have VA, VB, VR1, and VR2, all summing up to be 0. So if I go clockwise from the bottom left corner, I would have minus VA plus VB plus VR1 plus VR2 equals to 0. VA is a voltage source. VB is a voltage source. We don't need to express those voltages with anything. VR1, we use Ohm's law and express it as I1 times R1. And VR2 would be I1 minus I2 times R2. Make sense? Right? Well, at this point, we simply plug in the values. So VA is 10 volts minus 10 plus VB, which is 9, plus I1 times R1. R1 is 5. So 5 times I1 or 5 I1 plus R2 is 10. So 10 I1 minus 10 I2 is equal to 0. You combine everything that is possible and reduce the equation to this form. So I have 15 times I1 minus 10 times I2 is equal to 1. See, 5I1 plus 10I1 gives me 15I1 minus 10I2, and minus 10 plus 9 is minus 1. Take it on the other side, and you obtain plus 1. All right, correct? I'm going to label this as equation number 1. Equation number 1. Let's take a pause. Any questions? So far, so good. All right, let's go to mesh 2. Okay, mesh 2. This time I'll go a little bit quicker. We got VC. And then we got VB again here. R2, R4, plus minus, plus minus. Okay. In R3. Okay. I2. And then, of course, this is the shared branch, R2. So I1. Okay. And this is BA. Oh, VB, sorry. VB and VC. All right, apply KVL. What do we get? Starting in the bottom left corner, I have 2 voltages. So I'm going to write VB, VC, and VR2, VR3, and VR4, summing up to 0. Obviously, this is plus minus this way, plus minus, plus minus, plus minus. Okay, so VB is minus, VC is plus, plus VR2, plus VR3, plus VR4. Minus VB, plus VC. And VR2, of course, is the only other shared branch. So it would be plus, and this time we are in mesh 2, so I2 is positive, I1 is negative I2 minus I1 times R2 plus I2 times R3 plus I2 times R4. Okay. Plug in all the known values. VB is 9 volts. So minus 9 plus VC is 1. So plus 1. And I'm going to combine this. So R2 is 10. 10 times I2 minus 10 times I1 plus R3 is 5 times I2. And again, 5 times I2. So we obtain minus 10 times I1, and then I2 is 20. 20 times I2 is equal to 8. All this equation 2. Solve 1 and 2 with any method you choose. I will show you how I would solve this manually, since it's rather straightforward. You got equation 1, you got equation 2. It's a set of linear equation. So I'm going to say, let's say equation 1 multiplied by 2 and equation 2 multiplied by 3. That would give me 30 times I1 minus 20 times I2 is equal to 2. And then for equation 2, I obtain minus 30 times I1 plus 60 times I2 is equal to 24. Add these two together and you obtain 0 plus 40 times I2 is equal to 26. Therefore, I2 is 0.65 amps. And you plug this into any other equation, and I can obtain, let's see, I plug this into 30 times minus 20i. Okay, plug in I2. 30 times I1 minus 20 times 0.65 is equal to 2. Therefore, I1 is 20 times 0.65. I1 should be 0.5 amps. Okay. Anyone have a programmable calculator that they've programmed these equations in? Let me know if you obtain the exact same answer as I do. All right, let's take a long pause. You write it down. Let me know if you have any questions. The methods, the equations, anything. Again, once you have the set of linear equations, solve them using your calculators, manual methods, determinants, Kramer's method, Kramer's rule, MATLAB, anything. This is the procedure and the steps make sense. Okay. Now, at this point, obviously, we have only the mesh currents. We don't have the actual currents or the voltages across the resistors. But if we look at, ignore R2 for now. If you look at R1 and R3, if you look at R4, what do we see? They are not shared. There's only one mesh current flowing through there. So if that's the case, then that is the actual current that is flowing through that resistor. So if we take a look at R1, R3, and R4, we directly have the answer for the actual current flowing through those resistors, which is I1 and then I2 for R3 and R4. Yes. Okay, you answered your own question before. Was it about the direction or the? Okay. So then let's take a look at R2 because R2 is shared. So if R2 is shared, we just draw out R2, right? And so R2 is right here. And we have, what do we have? We have I1 coming down. We have I2 going up. So this is R2. So which direction is the actual current flowing through R2? First of all, they're both flowing in the opposite directions. So it would be either I1 minus I2, or it would be I2 minus I1. Make sense? Right? It's a difference of both. The reason it's a difference is because of the assumption we made at the beginning of our analysis, right? If they are both going in the same direction, it would be a summation. It would be I1 plus I2. But because they are in opposite directions, the actual current flowing through R2 would be a difference of the two. And how would we determine which? Absolutely. Whichever has the higher value is the dominant current. So I1 and I2, I1 is 0.5, I2 is 0.65. So it would be IR2 would be I2 minus I1, which is 0.65 minus 0.5, and be 0.15. Yep. And that is how, and once you have the actual current flowing through the resistor, you can find the voltages across those resistors. Make sense? Right. Okay, let's take a break. It's 11:03. Let's meet back at 11:08. 11:08. Let's take a 5-minute break. I'm here if anyone has any questions.